You can't go faster than the speed of light? Maybe yes. In this video we dive deep into the world of photons, space and time and clarify what the speed of light is and whether we can exceed it. Then maybe build a faster-than-light drive and fly to the stars. I promise you it's going to be really galactic, so be sure to stay tuned to the end, and if you like it, I'll be very happy if you give me a thumbs up at the speed of light and post a comment, because that's how we get the YouTube algorithm to display this important topic to even more people. Thanks a lot guys and welcome. Speed of light is the maximum. More is not possible. That's how we all learned it. But things are not quite that simple. The world of light, i.e. of photons, is incredibly complex and fascinating, and the thought blows my mind every time that we can change the passing of time the faster we move. I have therefore combined the most exciting topics about the speed of light in this video. In the following, you will learn what the speed of light actually is, whether perhaps gravity is faster than light, why the present is actually just a fake, and how researchers have managed to trick the speed of light. And at the end, we will even see that at NASA even already plans for a light-speed drive lie in the drawer. I would say we start with the speed of a photon and clarify what this ominous speed of light is all about. Hi guys! Oof, that was fast. Pretty much 299,792 kilometers per second. That is the speed of light. For the sake of simplicity, one often says 300,000 kilometers per second, and that is the fastest that is possible in our universe. But why actually? The question, why light is so incredibly fast, is one that mankind has been asking itself since time immemorial. There are already records of ancient Greek scientists and philosophers who have thought about it, because of course they could not calculate exactly how fast the light moves, but that it is incredibly fast, that they of course also noticed. For it one had to light only a lantern or torch and see that the light is immediately at the wall. Aristotle, the famous Greek philosopher, has therefore assumed that light does not move at all, because he thought it cannot be so fast. In fact, it is probably just everywhere. So he assumed that light is simply present everywhere constantly. In the 17th century, the discussion about the speed of light was a bit more eloquent. Johannes Kepler, the famous astronomer, assumed that light had a speed, but he claimed that the speed was infinite. He meant, look how fast the light is, it can be therefore only infinitely fast. His contemporaries Isaac Newton and Christian Huygens, by the way also two famous physicists, only said, no. So light is already very fast, but not infinitely fast, because an infinite speed cannot exist. And Isaac Newton has described the light as a particle stream, and this is after today's view already a very accurate description, because we know that light consists of photons, thus really represents a kind of particle stream. And by the fact that Isaac Newton could not observe this yet with most modern means, this was already quite good. In 1620, Galileo Galilei conducted an experiment to calculate the speed of light, because he also believed that light has a certain speed, and for this purpose he came up with a clever experiment. He and an assistant stood on different hills, several kilometers away from each other. Both had a lantern with them, and the idea was that Galileo turns on his lantern, and the moment the assistant sees that, he should turn on his lantern. And Galileo then measures the time difference as soon as the assistant's lantern turns on. Well, what can we say? It came on immediately, because the light from one hill was immediately visible at the other hill. Now, one could have concluded that the speed of light must indeed be infinite, but Galileo was a smart man. He realized that it simply means that light moves very, very fast, but not infinitely fast. The first really good measurement of the speed of light using purely terrestrial methods, that is, without taking other planets or eclipses, was achieved by the physicist Amour Fizeau from France, and he came up with a gear method. Really clever. Namely, the light sent through a moving gear to a mirror several kilometers away. This mirror reflected the light back onto the gear wheel and, depending on how fast the gear wheel was rotating, the light either flew onto one prong of the wheel or through the gear wheel through the prongs. And so, based on the speed of the gear wheel, you could calculate how fast the light is moving. Ingenious method, and Fizeau came to a value of 315,000 kilometers per second. That's not quite right. That's wrong by about 5%, but that's already a damn good result. But the one who is of course immortally associated with the speed of light is Albert Einstein. From him you surely know the famous formula E equals mc squared. The E in the equation stands for the rest energy and the m describes the mass. Both variables behave proportionally to each other, and what interests us now is c. C indicates the constant of the speed of light, thus approximately 300,000 kilometers per second. In other words, E equals mc squared describes the relation of mass and energy. In the special relativity theory of Albert Einstein, this speed of light, respectively c, plays a prominent role. In principle, this constant speed is the basic postulate of the special relativity theory. In it is valid, every observer measures the same constant value for the speed of light in a vacuum. 300,000 kilometers per second. It is important that the speed of light defines an upper speed limit. In special relativity, nothing can move faster than light. That is, also information or influences or other could ever be faster than the light. Practical example, imagine you are trapped in a black hole, for whatever reason, you have flown behind the event horizon. That is the limit where not even light can escape gravity, and you want to write a last message to your mom from there, "Hey mom, I am trapped in the black hole. Thanks for everything." Then this message also doesn't come out anymore, because if not even light can free from it and there is nothing faster, also nothing else comes out. I still owe you the answer why this is so. Albert Einstein, when he worked on the special theory of relativity, cut his teeth on a thought experiment. Namely, imagine there is a spaceship which flies with 10 kilometers per second through the space. A torch is glued to this spaceship. Now the light, which goes out from the torch, should move with a speed of 300,000 kilometers per second, speed of light, plus 10 kilometers per second the speed of the spaceship, or... Actually, these two velocities should add up, shouldn't they? But the answer must be no, because the result of the special relativity theory is just that the speed of light represents an upper limit. Einstein was able to solve this thought experiment in the end. He has found out that if an object moves through the space, it moves at the same time through the time. The concept of the space-time was born. So the realization that space and time are always inseparably connected. That is, the faster you move through space, the slower time passes. The faster I move through time, the slower I move through space. Thus, Einstein discovered not only space-time, but also the concept of the relativity of time. This means that time does not necessarily have to pass the same way everywhere in space. This means that the mass and the speed of an object influences the time. You probably know this from heavy planets, on which the time would pass more slowly, because they stretch the time more, or just really heavy objects, like black holes, which have such an influence on the time that the time passes there very slowly in comparison to the Earth. The time is therefore relative, and we reach the whole not only with mass, but just also with speed. What does this realization of the space-time mean now for the speed of light? Imagine a spaceship. The spaceship moves with a certain speed through space. Thus it moves through time and space. The faster than it moves through space, the slower time passes. Remember the link between space and time, space-time. That's right. That's what you do every day. By the way, you move through space and time. Your whole life is an adventure through space-time. Now let's imagine a photon, i.e. a particle of which electromagnetic radiation consists. One could also say a light particle. Such a light particle moves much faster than a spaceship with 300,000 kilometers per second. This speed has such a massive influence on the space-time that the time component is completely omitted. The time is slowed down so much that it stands still. So for the light, time does not exist. We can of course measure how long the light was on its way from another galaxy to us, but for the photon itself, this happens only in space, but not in time. So, since time becomes infinite from a speed of 300,000 kilometers per second, an increase is no longer possible. One could also say, at this speed, the interaction between space and time is exhausted. More is not possible. And this maximum speed is called c, and you still know it from Einstein's equation. In the meantime, the whole thing has already been proven exactly in several experiments. In 1964, for example, the physicist Bill Bertozzi from the USA carried out an exciting experiment. He accelerated electrons, negatively charged elementary particles, until they approached the speed of light. And he found, the faster you accelerate these things, the heavier they become, mysteriously. And at some point, above a certain speed, they become so heavy that they can't accelerate any further. You probably guessed it, the speed at which they become too heavy to move faster is 300,000 kilometers per second. So it's like an invisible wall that dictates the laws of nature. By the way, all this is not only theoretical, but it also has a very concrete impact on our lives. There are a lot of GPS satellites orbiting the Earth at a super high speed. And with these satellites, the effect of the speed on time, the so-called time dilation, must be taken into account. That is, if we didn't have this knowledge, if we didn't take into account the time dilation of satellites, then your entire mobile internet, with which we are watching this video right now, wouldn't work at all. So in the rough we know now what light velocity is, but somehow this gives rise to 1,000 new questions. For example, isn't gravity faster than light? Gravity works immediately. Did Einstein make a mistake? Let's unravel this. Whenever someone asks me what keeps me grounded, I always answer, gravity. What else? But if you start to think about gravity in more detail, then it quickly becomes mysterious. What is gravity exactly? The proof of a gravity particle is still not doubtful, and the explanation of the cause of this force is still as the biggest riddle of physics. But regardless of how and whether gravity can be explained quantum physically, is in any case somehow there. I believe at least. If someone of you floats gravitationless in the space while watching this video, write it to me with pleasure in the comments. One of the most confusing aspects of gravity is that it seems to be instantaneous. Or does the sun's gravity, which holds the Earth in place, also travel to us at the speed of light? To solve this riddle, we must dive a little deeper into Einsteinian physics. In his theory of relativity, Albert Einstein found that space and time are inseparable. Together they form space-time, and gravity affects space-time. The heavier an object is, the more space-time, which for simplicity's sake we can imagine as a kind of grid, is curved. You also influence the space-time just by your weight. Of course, this is not to say that you are fat. Another important insight of Einstein was that there is a maximum speed in the cosmos. This is called speed c. The theory of relativity states that the speed of light moving through a vacuum never changes. With rounded 300,000 kilometers per second, light has the highest attainable speed in the universe. And by the way, this is not only true for light, even if we always talk about the speed of light, but also for all other electromagnetic waves. How does gravity behave in this interplay of speed, space, and time? Isaac Newton, the discoverer of gravity, who, according to legend, had an apple fall on his head, believed that this force effect propagates without any time delay. But Einstein says in his theory of relativity, however, that gravity could move also only with speed of light. What is correct now? Does not the gravity of the sun affect us immediately? If the sun would disappear now, would its gravity then immediately be gone, or would it take about 8 minutes until we notice it? Because that is the time that also the light needs from the sun to the Earth. A team of researchers from the University of Columbia started a very clever experiment years ago to clarify this question once and for all, and they were helped by the planetary heavyweight of our solar system, Jupiter. Jupiter is twice as heavy as all the other planets in the solar system put together, so it really weighs a lot. Is that planetary fat shaming already? And this is what the researchers' experiment looked like. While Jupiter passed through the field of view, the researchers used several interconnected telescopes to observe the light from a quasar, the active energetic center of a distant galaxy. The gravitational force emanating from Jupiter minimally deflected the light from this quasar. So they used Jupiter as a gravitational lens. And from this, the scientists could then calculate the propagation speed of gravity, a method that was as simple as it was ingenious. And the result, gravity does not act instantaneously, it propagates at the speed of light. This was later confirmed by the first measurements of gravitational waves. Gravitational waves denote a kind of vibration of spacetime when two massive objects collide. For example, when two black holes merge, the grid of spacetime begins to wobble, and this wobble was first successfully demonstrated in September 2015 by scientists from the LEGO collaboration, after Albert Einstein had predicted it almost 100 years ago. Gravitational waves are only possible if gravity propagates with the speed of light. According to Newtonian physics, to which actually still some scientists adhered until then, such a wave would be inconceivable, because the gravity would reach the Earth immediately. So long speech short sense. Gravity moves as fast as the light, and although this was disputed for a long time, it can only be considered as proved. However, a few follow-up questions still arise. For example, if this is so, why can't light leave a black hole, but gravity can? However, this is based on a wrong conception of a black hole. The black hole does not emit gravitation from its inside, but the black hole itself is the gravitational field. In other words, gravity does not have to leave the black hole at all, the black hole itself is a frozen gravitational field. Gravity can be static, gravitational waves are as fast as light. After this excursion into the speed of gravity and light, I couldn't help but think of the movie Interstellar, which introduces the idea that there is an even more powerful, faster force in the universe: love. It can't be stopped even by the curvature of space-time. And therefore here is a nice quote for you, which supposedly, one must always be careful, comes from Albert Einstein. Gravity cannot be held responsible for the fact that people fall in love. How on earth can you explain such an important phenomenon as first love with the means of physics? Put your hand on a stove for a minute and it seems like an hour. Sit with this great girl for an hour and it seems like a minute. That's relativity. I don't know about you, but my brain is already bursting at the idea of this incredible reality of physics. But speaking of reality, the more we deal with the speed of light, the clearer it becomes. Reality is a complete fake. Ready for an identity crisis? Then pay attention now. This star island here is at a distance of almost 80 million light years from us. So when you see this galaxy, it means that the light from there has been on its way for 80 million years. In other words, you are seeing this galaxy as it looked 80 million years ago. This picture shows us the galaxy IC 4653 as it looked when dinosaurs still lived on Earth. That means the other way around. If alien astronomers observe our galaxy from there, they would see dinosaurs, unaware that this planet is no longer dominated by giant lizards, but by little hairy apes. Okay, so the principle is clear. Every look into space is a look back in time. Even some stars in our night sky don't exist anymore in reality, but already died in a supernova or passed away as a white dwarf. But we still see the star alive, because the light still reaches us after its death. Like you've been seeing your best friend for 2 years and then it turns out he's been dead for 5 years. Okay, now that sounds scarier than I thought. And that means that space telescopes like Hubble and James Webb are nothing more than extremely powerful time machines. With James Webb, we can see galaxies from about 13 billion years ago in unimagined detail. Incredible! And because the light from these far, far away galaxies is only now hitting the James Webb telescope, their appearance from 13 billion years ago is preserved, as a moment in time. That's incredible enough, but now it's even more incredible. This time travel is not only happening when you look into space, but also in your life right now. You are prisoners of time. The present does not exist. Everything you perceive in your life, all the great places you have seen, every kiss you have had, you have never experienced it life, not even in the moment it supposedly happened. Okay, I can see some of you saying,
has Tim become even crazier now than he already is?
Not at all. What I have just told is in the nature of the speed of light. Put yourselves once in a room 2 meters before any other object. Let's say 2 meters in front of a chocolate cookie. At a distance of 2 meters, the light from this chocolate cookie to you takes 6 nanoseconds. So you don't see the cookie as it is right now, but as it looked 6 nanoseconds ago. You can, of course, reduce this time span by taking the cookie and eating it. And it is the same with everything else that surrounds you. For example, you have never shared a moment simultaneously in the present with your partner. When you look into your girlfriend's eyes, it's no different than looking at the stars in the night sky and seeing them as they looked thousands of years ago. Only that in the case of your girlfriend's face, it's not millennia, but nanoseconds. But that doesn't change the principle. Everything that you perceive is already no longer real, has already been eaten up by the floods of time. Everything that we perceive is only an already dead part of the time. Nothing that you will ever perceive in your life is really real at this moment. I should become a motivational coach, but now it gets even crazier. People hold on tight. We now know that we do not have to see how it really is now. But things are at different distances from us. That means the light takes different amounts of time to get to us. Imagine you are standing outside on a meadow, you are surrounded by earth, trees, grass, clouds, and behind them of course the stars. The light from all these things takes different lengths of time to reach your eyes. You may see the trees as they looked 10 nanoseconds ago, the clouds as they looked a few hundred nanoseconds ago, and the stars as they appear centuries and millennia before. And yet, in your perception, all of this is real at the same time. This means that our complete perception of the world is not only always in the past, but that it is a mosaic of multiple pasts. What you perceive as the now is actually layer upon layer of light reaching your eyes from many different moments in the past. Your now is an overlapping mosaic of multiple pasts. What you think of as the real world existing simultaneously with you is a patchwork of different points in time. So to speak, a time matrix of different moments, which are already gone forever in the next moment. Like tears in rain. You never live in the world as it is. You only experience it as it was, a patchwork of past times, and we stand in the middle of all these already past moments, perceive them and form the illusion of our life from it. I've been thinking about this since yesterday, and the more I do it, the more incredible it seems to me. Based on this, one could ask the question if there really is a reality at all. After all, if everything we experience is already over and dead, then what is the truly existent present, that is, reality? I would be very interested to know what your thoughts are on this whole matter. Does a real present exist, or is there no real reality in view of the limited speed of light? Feel free to write your philosophical considerations in the comments, maybe we can get an exciting discussion going. I try to answer as much as possible. But what about the famous claim that it would not go faster than the speed of light? This is not quite true, as you can see for example in the cooling pool of every nuclear power plant. Here comes the explanation. Speed of light is the fastest, what there is this sentence one often hears. But it is incomplete, because it says nothing about in what the light moves. What is meant by this sentence is the speed of light in vacuum, and it is 299,792 kilometers per second. This is called the maximum speed c, and according to Albert Einstein's theory of relativity, this is the maximum that can be reached. By the way, not only of light, but also of the other electromagnetic waves. Now some of you will say,
I already knew that. Why is the strange man from the internet telling me this?
I tell this because it is not quite so simple. We have already heard that the speed of light depends on what the light is moving in. If it does not move in the vacuum, then it becomes slower. In water, for example, light travels only 230,769 kilometers per second. So it's even slower than I am when I smell something to eat somewhere. And it is also logical that the light then becomes slower, because the light particles, the photons, then have to fight their way through the water molecules. Of course, this takes time, just as you are certainly slower in the pool than if you were walking along the edge of the pool. Of course, the light is still immensely fast, and of course, we can still correctly speak of the speed of light, just not of the maximum speed c. And now an effect comes into play where the light particles can be overtaken, where something becomes faster than the speed of light. Charged particles can fly faster than the light if the light is slowed down by a medium, for example by water. Or something else, like for example vanilla pudding. Okay, I just needed an excuse to eat pudding in this video. Yummy! Cherenkov pudding. The effect I just described is called Cherenkov radiation or Cherenkov light. It can be observed for example in the water-filled reactor vessel of nuclear power plants, as you can see here. Electrons emitted by the radiation of the fuel elements, i.e. negatively charged subatomic particles, race through the reactor water so fast that the light emitted by excited atoms cannot keep up. A kind of subatomic wake is created, quasi a supersonic cone of light, which manifests itself in nuclear power plants by its kind of bluish glow. But I see already some of you say,
What the?
Let's go back to the pool. Imagine you are swimming your laps in the water. Waves created by your swimming motion. Wave crests and wave troughs. But with each additional swimming motion, you balance out the previous waves. All in all, the waves you create through your swimming motion completely neutralize each other. as each wave leisurely balances out the wave from before. They overlap each other, but you are certainly very good swimmers, so you get into the pool again and this time do a few laps at the speed of light. Your swimming speed is now much higher than the speed of the waves, because they logically do not arise with the speed of light. The waves can no longer overlap, because you are traveling so fast that there are always a few waves that are ahead of all the others. In this way you would have created a Cherenkov wave in the swimming pool, and you would probably be banned from the pool by the pool attendant. Simply formulated, one could say that the Cherenkov radiation arises when subatomic particles race through a medium, and are faster than the light propagating in the medium. The resulting subatomic Kiel wave is then faster than the speed of light in this medium. Some of you may now say that this is somehow cheating, because the Cherenkov radiation is then not faster than what is commonly meant by the word speed of light, i.e. not faster than the maximum speed c. It is only faster than the speed of light outside a vacuum. Right. But it's still interesting to realize that the speed of light is not the same as the speed of light. And now comes a special clue. Couldn't the principle of Cherenkov radiation perhaps be applied to the speed of light in vacuum? Couldn't there be radiating Kiel waves outside of media like water and custard? I mean, to hell with the laws of nature. Albert Einstein, never heard. That's exactly what researchers from Scotland at the University of Strathclyde in Glasgow wanted to find out, and their considerations are based, how could it be otherwise, on mysterious quantum physics. The part of physics that deals with the crazy world of the smallest particles and with which Albert Einstein already had considerable problems. In their calculations, the researchers determined how fast a particle would have to be and through what field strengths it would have to fly in order for Cherenkov light to be released in the vacuum in the form of gamma radiation. And indeed, they came to the conclusion that quantum fluctuation particles can slow down light when exposed to a strong magnetic field. This implies that energetic particles can also release Cherenkov radiation when they fly through strong electromagnetic fields. So say the researchers. But where could one find such an extreme environment where such a strong magnetic field is present? The answer, in the environment of the so-called millisecond pulsars. These are dead stars that only rotate around themselves at an inconceivable speed, emitting pulse-like bursts of radiation. Millisecond pulsars rotate once around themselves in only about 20 milliseconds. That's almost as fast as a politician rotates when you say the word tax cut. Some of these millisecond pulsars could already be detected, which is not so easy, because the things are super small, since the residual mass of the star is incredibly condensed. We are talking about sizes of only 15 to 20 kilometers. So super tiny for cosmic objects. But these millisecond pulsars give themselves away by gamma rays. And this is where the Scottish researchers' results now fit together perfectly, because part of this telltale radiation could be Cherenkov radiation. The researchers write, astrophysics thus provides us with environments where the vacuum Cherenkov effect could be observed. For protons of the highest energy cosmic rays, the high energy emission there is completely dominated by the Cherenkov process. That would fit perfectly, because in the past astronomers observed a mysterious gamma glow at the heart of many galaxies, including within our own Milky Way. A radiation in the gamma range whose source is completely unknown. Some astronomers try to explain this gamma glow with dark matter effects. The only problem is that nobody really knows what dark matter is. So far, it is a completely theoretical construct. Cherenkov radiation in vacuum, triggered by millisecond pulsars, could be a realistic explanation for gamma glow. But, and there is always a but, the vacuum Cherenkov radiation is also only a theory. For lack of now better research possibilities of these extreme environments around the pulsars, evidence is missing. But from my point of view it is an absolutely plausible idea, because they would not violate the theory of relativity. Because also the vacuum Cherenkov radiation would not produce velocities beyond the maximum speed c. Due to the quantum fluctuations in the strong pulsar magnetic field, the light particles are slowed down, and this in turn can then produce a Cherenkov Kiel wave which is faster than the slowed down light, but not faster than the maximum velocity c. The research team writes, our theoretical prediction is very exciting because it could provide answers to some fundamental questions. Among them, about the origin of gamma ray glow in the heart of galaxies. At the same time, it offers a new way to push fundamental theories to their limits and thus test them. At NASA, astronomers recently got a little sweaty. They have observed something in space that, according to the data, moves at 7 times the speed of light. Is that the Starship Enterprise or something? What they're so fast through the cosmos darts, you find out now. Let's start with an incredible fact. Neutron stars are such dense objects that a single teaspoon of such a star on Earth would weigh millions of tons. Thus neutron stars belong to the densest objects of the universe. They are the leftover cores of dead stars. Here you see a neutron star compared with the surrounding area of a big city. So they are not very big, but they are incredibly dense and heavy. And this is accompanied by a gigantic gravitation. When two neutron stars get too close to each other, they begin to race toward each other in a stellar dance of death, which ends in a violent collision in which gravitational waves and gamma rays are hurled into space. NASA observed such a neutron star collision with the Hubble Space Telescope in 2017. However, the analysis of the data took several years and was published only recently. The observed event has the very easy-to-remember name GB170817. Astronomers really have no talent for naming. So in this event, two neutron stars collided. Professionals also speak of binary neutron star mergers. This sounds very abstract, but there is something incomprehensible behind it. The collision not only emitted gravitational waves, i.e. caused space-time itself to wobble, but also created a black hole. Around the black hole, a rotating disk, a so-called accretion disk, was formed, in which matter accumulated, which was caught by the gravity of the black hole. In such an accretion disk, extremely much energy is produced, and it can come to the fact that this energy is fired in the form of violent eruptions, so-called jets, into the space. NASA has succeeded in analyzing the jets of this neutron star collision in the same way. And the result probably left the scientists pretty wide-eyed, because the measurements showed that the radiation moved at 7 times the speed of light. And call me conservative, but actually this is not possible. We know since Albert Einstein that the maximum speed c as a natural constant is the fastest that can be achieved in our cosmos. The speed of light in vacuum corresponds to this maximum speed c. 7 times the maximum speed would pretty much throw everything we think we know about light and relativity out of the window. Let's play a little game. Before I present the researchers' explanation for this curious measurement, why don't you write in the comments how you would explain it? How can the rays seem to travel at 7 times the speed of light? Is our understanding of the speed of light wrong? Was there a measurement error? I look forward to your most exciting theories and try to answer as much as possible, I promise. First, however, they were delighted that Hubble can make such precise measurements at all. Involved astronomer Kunal P. Muley says, "I'm amazed that Hubble could give us such a precise measurement that rivals the precision of powerful VLBI radio telescopes, distributed around the globe." It was also the first combined detection of gravitational waves and gamma rays in the merger of a binary neutron star. So either way, an absolute historic achievement by NASA and the Hubble telescope. But what's the deal with the speed of light? The answer is superluminal motion.
What does that mean again?
Superluminal motion is an effect that can occur when light approaches our observing instruments, and creates the illusion that the light is moving at a speed higher than the maximum speed c. The light is then emitted by the neutron-stone collision jet. As the jet of the neutron-stone collision approaches our Earth at nearly the speed of light, the light it emits later has a shorter distance to travel each time. One could say that the jet chases its own light. In reality, more time has passed between the emission of the light by the jet than the observer thinks, and this then leads to the fact that the speed of the object is overestimated, and in this case it seems to exceed the speed of light. Okay, but honestly, who understood that now? I thought so, therefore here again a little bit more in detail. Imagine the black hole with its accretion disk. There, photons, i.e. light particles, are shot into the space, which move almost with maximum speed c. These photons live in a relatively small space. So these photons live in a relativistic world. For them the time does not exist, because the faster one moves, the more this influences the time, and then at maximum speed the time does not pass at all. The radiation waves which reach us from the neutron-star collision move almost with maximum speed. The time passes therefore only quite minimally for them. Means, a photon which is shot off there today will reach the Earth insignificantly earlier than a photon which is shot off only in a month, Because for these photons, categories like today, next week, or in a month do not exist at all anymore due to their speed. In other words, the time span between such two photons is much shorter than 1 month, which gives the impression that the beam is moving faster than the speed of light. This is superluminal motion. I know, very complex. If you have any questions about it, and if anything is not clear, feel free to post them in the comments. Anyway, NASA was able to calculate how fast the radiation waves actually move. Involved researcher Wenbin Liu says, "Our result suggests that the jet was traveling at least 99.97% the speed of light when it was launched. So much slower than 7 times the speed of light, but to be honest, still impressively fast. And the idea that time hardly exists for photons, and that relativistic effects make us believe that there is something higher than the speed of light is simply fascinating, isn't it? A cosmic prank, so to speak. And definitely more interesting than anything you can see on the usual prank channels on YouTube. By the way, the first precise measurement of the speed of light was made in 1676, when the Danish astronomer Ole Romer used Jupiter's moon Io. Using the eclipse times of the moon as a function of Jupiter's distance from Earth, he was able to verify the speed of light. But now we come to the core of the photon. Is it perhaps somehow possible to break the speed of light, to really create something faster than light? Plasma researchers at Lawrence Livermore National Laboratory say yes. Here is the incredible experiment. One of the constants of nature is the maximum velocity c, colloquially known as the speed of light. Albert Einstein stated in his theory of relativity that the speed of light moving through a vacuum never changes. At a rounded 300,000 kilometers per second, light in a vacuum travels at the highest speed imaginable in our universe. Speed of light, however, is not really an accurate term for it, for 2 reasons. First, not only does light reach this maximum speed, but so do all other electromagnetic waves. Second, light can also be slower, depending on the medium through which it is traveling. In water, for example, the speed of light is reduced to just under 231,000 kilometers per second. So light speed can vary, only in vacuum it reaches the maximum speed c. So far, so good. But some of you are now surely asking yourselves,
But why do you have to obey the laws of nature? I hate rules.
Personally, I am also very allergic to rules, but we have to abide by them. And so, of course, do the photons, the particles of light. But there are properties of light that do not play by the same rules. Physicists at Lawrence Livermore National Laboratory in the US have succeeded in accelerating waves consisting of groups of photons to faster than the speed of light. Sounds incredible and is also a bit tricky, but we'll go through it step by step. The researchers first created a hydrogen-helium plasma, i.e. an ultraheated mixture in which the electrons are torn out of the atoms to form an ionized gas. You probably know the basic principle from those fancy plasma spheres that were all the rage in the 1980s. To create the plasma, the researchers bombarded the hydrogen-helium mixture with a polarized laser beam. Then they directed a second laser beam at the plasma, and exactly where the paths of the 2 beams crossed, the second laser pulse slowed down in response to a change in the refractive index of the plasma. So in other words, the slowdown was caused by the interaction between the 2 lasers and the plasma. The laser pulses, in turn, have a horizontal and a vertical component, and the physicists measured the time difference between these 2 components of the laser beam. By slightly changing the exact alignments of the 2 laser beams, they could adjust the time difference between the horizontal and vertical components of one laser beam. The researchers played around with the adjustment of the laser pulses, and found that they could decrease the speed of the one laser from 0.995 c, almost no speed, by -0.3 for c, or increase it by up to 0.12 c. The researchers also measured the time difference between the 2 components of the laser beam. I'm not good at math, but if we do the math, 0.995 c plus 0.12 c, then we get a value higher than AC, higher than the maximum speed c, higher than the speed of light. The tip of the pulse moves faster than c. What now? Is Einstein now completely disproved, all his theories at the end, the previous physics not even worth the sheet of paper on which it was written? Not quite, because we're talking about the speed of light pulses, which are whole groups of photons. And although most people don't know it, the speed at which light pulses move through a material can be very different from the speed c, which is the speed at which light does not move in a vacuum. This speed of the light pulses, called the group velocity, can be either higher or lower than c. And this has a strong influence on how the shape of a light pulse spreads and distorts as it moves through a particular material. To put it more simply, the individual photons still move at their usual pace, but their collective dance accelerates. You probably know this from the club. When you are alone on the dance floor, you move rather cautiously. But when everyone else starts dancing and the DJ starts the Backstreet Boys and the 10th gin and tonic is in, then it's on.
Backstreet's back, alright.
It all sounds great. So when do we start building spaceships that take advantage of this group velocity and take us to the stars? This will probably be a bit tricky, because for more complex processes, like propulsion or information transfer, the factual speed of the photons is relevant and not the group speed. And as we have already learned extensively, the individual photons cannot crack the maximum velocity c. As spectacular as the experiment at Lawrence Livermore National Laboratory is, it probably won't give us faster-than-light propulsion for now. But that doesn't mean we can't use it to achieve other spectacular technological breakthroughs. For laser technology in particular, these breakthroughs are incredibly interesting. Using plasma currents to amplify or change the properties of light allows us to build advanced, high-tech lasers, which in turn are essential for a whole range of future technologies. Clement Goyon, head of the experiment, said, "Slow and fast light is just the tip of the iceberg. The ability to predict plasma properties and use them to our advantage is critical for high-energy laser experiments in high-energy density physics and inertial fusion. We would need such lasers, for example, to power up particle accelerators or to improve nuclear fusion plants. This is a technology that could potentially provide us with almost infinite energy at some point in the future, which in turn is crucial for propulsion systems in space travel." In a roundabout way, these plasma faster-than-light experiments may give us a kind of hyperdrive like in Star Wars. I know it's a relatively tricky and complicated topic, so I'd like to answer as many questions as possible about the speed of light in the comments. What is still unclear, what you always wanted to know about the speed of light? Write me all your questions here in the comments. I'll try to answer as many as possible, I promise. So we see that the speed of light in vacuum with a little trickery is perhaps not set in stone as the fastest after all. And on cosmic level, we could overcome it perhaps also by turning the space-time around, like a worn pair of underpants or something. Now it's really getting wacky, so buckle up tight and let's reverse space-time. Now it's all about space-time dimensions. So 2D Mario from the old Super Nintendo is unfortunately out of the question today. As far as we know, there are at least 4 dimensions in the universe, 3 spatial, which we hope you can all perceive, and 1 temporal, which we can't see, but for which we nevertheless have some kind of feeling. Together, these dimensions make up space-time. And my speed through space affects time. This is one of Albert Einstein's revolutionary findings within his theory of relativity. But what if we could just change the signs and stay within the framework of physics? More precisely, if we make 3 spatial dimensions and 1 temporal dimension, 3 temporal dimensions and only 1 spatial dimension. What? Sounds wacky, but that's exactly what a team of researchers from the University of Warsaw is now proposing, and they're calling it, building on the number of dimensions 1 plus 3 speed of light. Lead researcher Professor Andrei Drogan says, contrary to our popular belief, time and space are amazingly similar according to relativity, and the only mathematical difference between them is the minus sign somewhere in the equations. In other words, if we were to theoretically exceed the maximum velocity c, perhaps the relationship between spatial and temporal dimensions would simply be reversed. But I can already see the question marks above your heads, so let's break it down by throwing another term at you. Superluminal observer. Sounds like a new Marvel superhero. The superluminal observer is a theoretical observer of at least apparent faster-than-light speed. Surely you know the warp drive from Star Trek? Here, spaceships can de facto arrive at another location faster than the speed of light, but remain completely in line with physics, because in reality they are not moving fast at all. Instead, space is warped around the spaceship, while the spaceship itself remains motionless in a warp bubble. By using this space curvature trick, you can trick the maximum speed without hurting it. Now imagine that you have made a career jump and suddenly you are an officer of the USS Voyager. During the warp jump, you look out the window. What would you see? At that moment you would take the perspective of the superluminal observer. This is also beautifully depicted in my favorite science fiction movie Interstellar, where the spaceship travels through a wormhole and the crew has very strange superluminal experiences. But it is important to emphasize again that the superluminal observer is in reality not faster than light, because he sits comfortably in his warp bubble, but could perceive the area outside the warp bubble superluminal. And this makes the construct of the superluminal observer a very nice idea, which in a way connects two very different sides of physics, namely, Einstein's general relativity and quantum mechanics, which is the physics about the very strange behavior of subatomic particles at the smallest scales. But more on that in a moment. What the researchers from Poland have now asked themselves is basically, what does space look like for the superluminal observer? And this is where the above-mentioned sign reversal of the relativistic equations comes into play. We remember, Einstein assumed in his special theory of relativity that the speed of light in a vacuum is constant regardless of the motion of the source, or the observer, and that the laws of physics are the same for all non-accelerated observers. Professor Drogon says, this principle applies to observers moving relative to each other at velocities below the speed of light. But there is no reason why observers moving relative to the described physical system at velocities greater than the speed of light should not be subject to this principle. For the superluminal observer, therefore, suddenly 3 time dimensions would open up and he would see the cosmos aging differently in all 3 dimensions. How this would look exactly, that exceeds unfortunately my Homo sapiens brain, which is designed evolutionarily on 3 space dimensions and only on 1 time dimension. But perhaps the closest you can really imagine it is like the scene in the movie Interstellar where the protagonist can communicate across the boundaries of space and time within a so-called tesseract. A tesseract is a 4-dimensional hypercube, and perhaps we would enter just such a one if we succeeded in taking the perspective of the superluminal observer. In the tesseract, the laws of nature are not violated, but simply the signs of space and time have turned into their opposite. Like an equation that works both ways. Or as Professor Drogon says, time is superluminal observer becomes space of subluminal observer and his space becomes time. The corresponding signs must therefore be reversed. In other words, space and time of the regular not light-fast observer become quasi-cross-relative to the time and space of the super-light-fast observer. Phew, my head feels so slowly already superluminal. As with Interstellar, such a superluminal view could give humanity an immense technological boost, because the researchers believe that their consideration could be a link between Einsteinian physics and quantum mechanics. This is because they think that the rules of relativity transform into quantum physical phenomena in the 1+3 frame where dimension reverses. Namely, in quantum physics there is a special phenomenon called superposition. This means that subatomic particles can be in multiple states at the same time, and this situation, amazingly, does not change until it is measured. A famous example is the thought experiment of Schrödinger's cat, with which the quantum physicist Erwin Schrödinger wanted to show that the quantum physical rules cannot be transferred to the world of classical physics, because, as far as I know, a cat cannot be dead and alive at the same time. But in the superluminal world, with its 3 time dimensions, the observer could now see that objects move according to the principle of superposition on several time bands at the same time. Thus the 1+3 framework could be a connection theory between relativity and quantum physics. Something that modern physics is desperately looking for. Okay, I admit, that was really heavy stuff. So let's relax with a little round of questions. Which is your favorite science fiction movie? Also Interstellar, like mine, or something else? Write me in the comments. I'm very curious about your answers, because I urgently need new movie tips for the weekend. Phew, feels like there are photons whizzing through my head. Are you still receptive? Then we can still clarify how we can pack all this collected knowledge about the speed of light into a drive. NASA has an idea. This is how we build the helical drive. I don't know about you, but when I look up at the stars at night, I am always overcome by an overwhelming mixture of fascination about the beauty and size of the cosmos, but also disappointment about the fact that I will probably never get to see these alien systems and planets. Unfortunately, the distances in space are simply gigantic and cannot be bridged with conventional propulsion systems. Our neighboring star alone, the closest star to our solar system, Proxima Centauri, is 4.2 light-years away from us. Our current drives are therefore not even close to being sufficient to visit the nearest exoplanet Proxima b. So do we have to give up hope that we might be able to spend our next vacation on Proxima b instead of Hawaii? There is hope, because a NASA engineer says he has developed a blueprint for a light-speed engine. David Burns has developed a thruster concept that could theoretically accelerate to 99% of the speed of light, and without any fuel at all. David Burns calls his concept the helical engine, and it basically takes advantage of mass-changing effects that occur at near light speed. It's a bit tricky, but let's go through it together and understand it. Imagine the following construction: a box is on a frictionless surface. Inside the box is a rod on which a ring can slide. When a spring inside the box gives the ring a push, the ring slides along the rod in one direction while the box bounces back in the other. When the ring reaches the end of the box, it bounces back and the recoil direction of the box also changes. This is the principle of action and reaction, also known as Newton's third law of motion. It is precisely this action-reaction law that is also used by classic rockets, which fire fuel in one direction in order to rise in the other. So far, so unspectacular. In our box, this would simply cause the box to wobble back and forth evenly. The ring always gets the same recoil from each spring. With such a box, we certainly won't get to Proxima Centauri. But what would be, if the mass of the ring would be much bigger, if it would slide in one direction than in the other? Then the box would get a bigger push at one end than at the other. The action would outpace the reaction and the box would accelerate forward, toward infinite distances. But I can already see the skeptical looks from those of you who always paid close attention in physics class. If the action exceeds the reaction without external influence, wouldn't we have violated Newton's third law and thus one of the principles of physics? No, because the helical drive takes advantage of effects that occur near the speed of light. Einstein's special theory of relativity states that objects gain mass as they approach the speed of light. This effect must also be taken into account in particle accelerators such as the Large Hadron Collider at the CERN Research Center. Exploiting this effect is at the heart of the helix drive, but of course the whole thing doesn't really work in space with a box, a rod, and a ring. Then you could build the thing at home, which would be cool, but you'd probably have to replace the ring with a circular particle accelerator in reality, where ions, electrically charged atoms, can be rapidly accelerated to immense speeds and decelerated just as quickly. And what do we do with the box and the rod? We don't need them at all. Instead, we build the particle accelerator in a spiral shape. It then functions as a box, rod, ring and spring. With such a spiral particle accelerator, which would bring ions to near the speed of light, we could thus make helical propulsion a reality through the mass-affecting effect of the speed of light. Okay, where can I change my vacation from New Zealand to Proxima b? David Burns describes it like this: the thruster accelerates the ions, which are enclosed in a loop, to moderate relativistic velocities and then varies their velocity to slightly change their mass. The thruster then moves the ions back and forth along the direction of motion to generate thrust. This all sounds very well thought out and sophisticated, but before you book a package vacation on Proxima b, wait a moment, because there are a few practical problems. Some researchers did some calculations and came to the conclusion that the spiral-shaped structure would have to have gigantic dimensions. For the concept to work, it would have to be about 200 meters long and 12 meters in diameter. That would certainly still be feasible, but the biggest problem is the amount of energy required. For the helix drive to work, you would have to put huge amounts of energy into it, because it needs 165 megawatts of power to generate just 1 Newton of thrust, which is about the force needed to type on the keyboard. so you would already have to invest large amounts of energy to get out even the force of one tap on the keyboard. And, of course, you would need much more force than just a keyboard tap. You would need at least as much thrust as I generate when I write the scripts for my videos. On the other hand, the amount of energy that has to be put in could also be reduced in the vacuum of space. Nevertheless, it will probably remain that the helix drive remains extremely energy inefficient. The most important thing is, the helix drive would work and it would not violate the action-reaction principle by applying Einstein's special relativity theory, and this alone sets it apart from similar concepts, such as the so-called EM drive, which is based on the use of microwaves, but according to prevailing opinion violates Newton's laws. So it will be some time before we really have a practical helix drive that can take us to the stars. In particular, we need breakthroughs in energy generation for this. We might be able to do that through nuclear fusion, but it's a promising first concept and you have to start somewhere and then build on it. Personally, I have no doubt that our human spirit of discovery will eventually take us to distant exoplanets. I would be very interested to know where in space you would like to travel. Assuming the helix drive becomes reality, which destination, which exoplanet, which star systems would you head for? Feel free to write me in the comments, I'll try to answer as much as possible. Wow, that was a wild journey through space and time, and I hope that the very abstract concept of the speed of light has become a little clearer. If so, I'd love for you to help me reach my big goal of 15,000 subscribers with speed of light. There are not many left, so if you watch the video and shockingly have not subscribed yet, by all means press the subscribe button. It's completely free and helps me immensely. Let's come, however, to other worlds which perhaps already travel the space with light speed for a long time. Maybe there are species out there in the universe which are not built on carbon like us and are already much more developed. Life forms could be based on many different materials, so for example silicon. Everything to the silicon aliens you find in the indicated video, and if you would like to support my work, then treat yourselves in my space store a fluffy plush black hole that one can turn to the white hole. Every purchase helps me a lot to continue the channel. Otherwise, I would say, see you in the next video. Take care guys.